Okay, welcome to topic 6. This is about the power equation. Okay, here is suggested reading in chapter 14 of the book. And in this topic, we'll focus on determining relationships between input and output forces and torques. Okay, so to this end, we will use an energy-based approach, leading us to the power equation for the mechanism. Okay, so basically we have done position, velocity, and acceleration analysis, and now we're ready to get into forces and torques or moments. In this topic, we're going to use energy and power arguments to find external forces only. So not internal forces. Using this approach, I'll emphasize you can't really tell much about the forces that are going on inside the mechanism. The internal forces, like the force inside a link and that you need to analyze if it's about to yield or break or something like that, or buckle. This approach you can't use to determine that. Just the external forces, the forces you externally apply, and that the mechanism as a response externally, applies to something external as an output. So if you don't know what internal and external forces are, we'll talk about those. But just to emphasize, energy lecture, dealing with external forces, okay? After this topic, topic 7 will be different approaches for finding dynamic and static forces that are both external and internal, okay? So, but this is a useful one to understand. Okay, so let's do fundamental principles. A lot of these principles you already probably knew from high school physics or at least freshman year. But let's do a review with some conventions and in the context of this lecture. Okay, so work or energy, right? The work done by a force on a body. Okay, so imagine this body. It's an arbitrary potato-like shape, and it's got a center of mass here. That's what G is, the center of mass, where is all concentrated there. So that's a point of interest that kind of represents the whole mass of the potato. And this guy's got a moment on it, and we see a force is applied at this point A, okay? And apparently this is the path of A, right? So we know that the potato is moving along this path, or at least that point A on the potato is moving along that path. And we know we're applying a force in a direction that's not along the path. And of course you can do that. Oftentimes objects, just like acceleration doesn't always point along, tangent to the path. In fact, it rarely does. Force, which is F equals ma, right? Force also doesn't always point tangent to the path, okay? So, okay, but let's say we're applying this force at point A, all right? And it's moving along this path where each little increment is a dr vector, okay? Of the point A. So like this dr vector with an underscore there at A. And that's an infinitesimally small mass that basically just captures the direction that's tangent to the path. Okay? And so the direction is tangent to the path, but the magnitude is infinitesimal. And then you've got a finite force, which is also, of course, a vector with a magnitude and a direction. Okay? And even though the force doesn't necessarily have a location, we know it's acting at A. Okay? Okay, so, and by the way, the knowledge of that is in the R. That's it's at point A through R. Okay, so if you want to find the work along this whole path from some first location to some second location, you take the dot product of those, the force and the infinitesimal increment, and you sum them all up from where you started to where you ended. Okay, and so what that'll of course do, the dot product, and you take the magnitude of F times the magnitude of dr, which is infinitesimally small, times cosine the angle between them, and that will basically find the component of the force that points in the direction of the infinitesimal dr vector, and times it by that. Okay, and then when you sum it up, you get a finite value that's the work. Okay, and I'll emphasize that's an external force that we, externally put and applied to it. Okay, so this is the external work applied from forces. And then, of course, you'd have to add that to the external work applied from the moments. Okay, and if this was a 3D scenario, you'd have a moment vector that you would dot product with the d theta j. It would be a vector, which just basically captures the direction and magnitude about which the body is rotating. Okay, again, it doesn't say anything about the axis, the location of the axis that it's rotating. It's just the magnitude and direction, and you dot product those. But because this is everything in this topic is just like this course is limited to two-dimensional planar bodies. When you dot product those, first of all, the moment and the direction of the rotation are always in or out of the plane, perpendicular. So they're already going to be pointing in the same direction, so you don't have to dot product to find the component of m in the direction of the rotation. So you just take that magnitude and you times it by this little increment, and again you sum it over its entire finite range of rotation. Okay, and you'll get a work caused from the moment as well, and you can add those together to find the total external work applied to that potato to move it along that path and rotate it. Okay. Okay. All right. So that's work. Okay, and of course it's in units of Newton meters. Okay, this is force times the distance, right? And that's or joules, of course. That's energy. Okay, so kinetic energy of a rigid body is defined, we'll call it T here, and if it's a link J, it's the kinetic energy of that link J. Okay, and many of you know from high school the kinetic energy of a body is 1/2 mv squared, or the speed or velocity squared, or the magnitude of the velocity, which is the speed squared. But just a little nuance, the question is which speed, right? Because if you've got this potato and say it's rotating, flipping through space and translating, every velocity vector at different points could be very different, especially if it's rotating. Like say it was rotating on this axis, well at that point it would be zero velocity and all the other ones would have different velocities, right? According to the velocity difference equation. So the question is, what speed do we square here? Well, it's the representative speed, which is basically the speed of the vector, the magnitude of the velocity vector at the center of mass. Okay, so that's the one that's going to matter. If you need to find some representative property of any body, usually do it at the center of mass. Okay. Okay, so that's how you find the linear component of this. Okay. And but there's also a rotational component. There's angular kinetic energy, right? Caused not just by the linear translation, but the rotation of the body. So to do that, it's no surprise instead of 1/2 mv squared, it's 1/2. This is the mass moment of inertia, okay, which is essentially, right? It's the integral of r squared dm, right? If you recall from high school math, where it's basically angular mass, and it depends about what axis it's rotating around, and then of course you times it by the angular velocity or the angular speed, the magnitude of the angular velocity vector squared. Okay, so you can see the analog here. That's like the rotational mass. That's the linear mass. That's the linear velocity, and that's the angular velocity. So it's basically the same thing. The interesting thing to note, though, is mass here, it doesn't have like a representative point. It's just how much mass is in the thing, right? But the velocity needs to be at this specific point, at this representative point. Whereas here it's switched for angular stuff. You actually don't need to know the axis about which it's rotating. You just, because angular velocity, everything in this, every point on this, if you assign a coordinate system to every point, you'll find they all rotate the same amount, right? It's not like, it's independent of where the axis is, right? They all rotate the same amount. So instead of linear velocities being all different at different points, you need something representative here. They all rotate the same amount. So there's there's no, just like mass doesn't need any special location, angular velocity doesn't either. But conversely, just like linear velocity did need a special point, you need to take the mass moment of inertia about an axis in this point right here. And of course, because it's a planar scenario, omega is always perpendicular to the plane, and you're always taking the axis that comes perpendicular to the plane through the center of mass when you're calculating the mass moment of inertia. Okay? So those are just some interesting things to notice. Okay. So that's kinetic energy, the energy of motion, the energy in a moving body. Obviously, things that move faster and faster have more energy. You certainly wouldn't want to get hit by a speeding train versus a train that's just inching along, right? It have a lot more energy. Well, this is potential energy, and many of you know that that's kind of the energy of stuff stored up in something. Like you lift a rock high above your head, it's got a lot more energy to crush something than if you just, if it's sitting there on the ground. Right? So, or a bow and arrow, as you pull back a bow, you store the energy in there, and it's just waiting as deformed strain energy to launch the arrow, right? So, just a review, you all know from high school physics that it's essentially the mass of the link, J, right, times G, 9.8 meters per second squared, right? If you're on Earth, right? So that's the acceleration on the surface of the Earth. Okay, but then you times it by the height above some datum line, which is y gj. Now, of course, say your datum line is here, say that's the ground, so to say, and which height do you do it from there to there? Well, again, you do the representative height from the perpendicular. If you take a line that's perpendicular to whatever the datum is that goes through that center of mass, the distance between there and there would be that height. So you use, again, that center of mass as the representative location to calculate the potential energy, gravitational potential energy of a body. Okay. Now, the datum line could be arbitrary, right? Are you going to use the ground? Are you going to use the top of a table? So usually people don't talk about potential energy of something as much as they talk about the change in potential energy, because that starts being absolute, right? But if you define the datum, then you have an absolute potential energy, okay? So the potential energy of a spring, this is so the first one was the gravitational, and that's like the analogy of lifting a rock above your head versus a rock on the ground. But you can also store strain energy by deforming things. And so say you have a spring that started at some length L naught, okay, but then you stretch it to, say whatever its length is that you stretch it to is L, well then you can find out how much it's stretched, either compressed or stretched, right, if you take L minus L naught and define that as delta, okay? And how much that displacement that it's been stretched or compressed, delta, you take that and square it and times by 1/2 K, times delta squared, okay? And that's the spring potential energy, or how much energy is, has the potential to be converted into kinetic energy. Is it right? If you let it go, it'll spring out and convert into kinetic energy. Okay, so, and you all remember that. And by the way, all these derivations are in high school physics textbooks and stuff, if you need a refresher on those. Okay, dissipative energy. So we've talked about kinetic energy, the energy of motion. We've talked about the energy of potential energy, stored up energy waiting to be released. And now there's dissipative energy, which is the energy that is dissipated from a body through heat, right, essentially, okay? So when you have a dashpot, say you have like a syringe or something that's filled with honey, here's a schematic on the right-hand side, and you have the distance between the two. You can imagine, unlike a spring where the force that it resists is proportional to the displacement, it's actually proportional to the velocity that you're going to pull it, right? So instead of it being F equals kx, where it's a function of x, the displacement, dashpots are a function of the velocity, and they're a viscous element that dissipates heat through the friction in the honey inside or the viscous material. Okay, so, and of course, you could stretch this to multiple distances, and if you let it all settle, there's no force on it. But if you push it slowly, there's a little force, and if you jam it in hard with a high force, then you can get higher velocity. So forces depend on the velocity here. So to find the work or the dissipative energy, the dW, the little increment of work created from a dashpot, or energy dissipated, you could say, you'd take the damping coefficient C, which is like, I said F equals CV is what a dashpot is, right? Where the velocity is the time derivative of this displacement r. Okay, so r is the distance between them. You take the time derivative, which has a dot above it, and that's the force of the dashpot. And then you times it by dr, because force times dr is going to be, and of course they're going in the same direction in this instance, right? So you don't have to dot product, but of course the energy is force times displacement. So C r dot is force times dr is displacement, and you've got your dashpot dissipative energy. Okay, so there's other ways you can dissipate energy to heat, that aren't involving viscous fluids, the particles, and they're rubbing past each other as they move around the plunger and flow. There's also dissipation due to surfaces rubbing together from friction, right? And so hopefully you all know how friction works. If you have a normal force here, which is basically better captured by the force that the ground pushes up some together on the body is really the normal force. And that normal force multiplied by a coefficient of friction is the force that it can resist due to excuse me, sorry about that, due to friction, right? Now, hopefully you know there's a static and a kinetic coefficient of friction. So the static coefficient of friction is larger than the kinetic coefficient of friction typically, which is why it's harder to get an object going. When you first start pushing on this, increase the force, it'll always match you and push in the opposite direction until you reach the max force just before it slips. And that force that it resists just before it slips is n times the static coefficient of friction. And then once you finally exceed that and push it beyond that force, as it starts moving now it switches to the kinetic coefficient of friction, and that's a lower force, so it actually becomes easier to continue pushing something than to start pushing it. Okay, but the energy dissipated from that friction force, friction coefficient times n, normal force, can be found by times that by dr, the little increment, and that's the dissipative work, or the amount of energy that dissipates due to the friction. Okay, so those are the fundamental principles. Let's now introduce the power equation. Okay, so before I introduce the power equation, let's talk a little bit about the work-energy equation, which is essentially the net work, meaning basically the work done by external forces and moments. Say I load it externally. Say I take a mechanism and I put all these forces on the links or moments on the links, or maybe there's an output load that the mechanism is doing to something else. Those things from external bodies that are acting on the mechanism, or the external forces, you find the work done by those bodies, and that equals the change in kinetic energy of the mechanism plus the change in potential energy of the mechanism plus the change in dissipative energy of the mechanism. Okay, so that's, hopefully you all know that basically from high school physics. If you don't know it now, you do. But there's some nuances in this. The equation represents the mechanical potential and dissipative energy of the system and the work performed on the system as a whole. The net work acting on the system of the rigid bodies by internal force of contact with rigid bodies at smooth joints is 0, and therefore do not need to be included in the work term. So, well, first of all, anytime you see smooth joints, that basically is another way to say they're friction-free. Of course, if the joints did have friction, it would be that friction, the energy due to friction, would be considered in the change in dissipative energy, as you know. So that is already taken into account on the right side of the equation. But what this is really saying, of course, if the joints are smooth, friction-free, there is no dissipative energy from that. And so you don't need to consider it. But what this is saying is the internal forces at the joints. If you have two links stuck together by a pin joint, this one's putting force on that, this one's putting forces on this one. And those internal forces, or if you cut a beam, a link in half, and you see the internal forces from the stresses inside, you don't consider those forces, those internal forces that are going on in the mechanism, to keep it from falling apart and, to keep it working together as rigid bodies in a mechanism. You don't consider those forces in the work equation, okay? So they're not considered in here. You can't find them, which is why, I told you at the beginning of this lecture, I'm going to show you an approach that you can use to calculate the external forces and loads and moments on a mechanism using this equation, but it tells you nothing about those internal forces, okay? Okay, it does not include forces due to gravity and springs, the work here, because those are already taken in consideration with the potential energy, right? So, you might think, oh, gravity is an external force. The Earth, is externally putting that force on. Well, you don't consider that a force in the network side. It's already taken into account in the potential energy, the gravitational potential energy. So you don't use that force for that. You put it in the potential energy one. And then, of course, springs, they're in the potential energy side as well, or deformations. Okay, the third point, it does include externally applied forces and couples, of course. That's what it includes. That's the network, okay? For externally applied forces, care must be taken to include only the components of these forces that are tangent to the path at which they act. So remember, when you're defining this left side, make sure you look at the first slide, or that slide where I introduced what work is from both a linear force perspective and a moment perspective. Okay, remember where you take F dot dr, that will make sure you consider the force component along the path, because that's what you use. That's what this is saying. But if you use that dot product, you'll always be fine. Okay, and again, you'd only need to worry about the dot product with the moments if it was a 3D scenario, but for planar ones, you don't need to worry about it, right? But you may need to worry about the sign, right, for planar scenarios with moments. But you don't need a dot product. Okay, the so-called power equation is determined from a time differentiation of the work energy equation. Okay, so if you just divide both sides basically by delta T, then, of course, the change in work divided by time, work per time or joules per second, that is, or of course, Newton meters per second is the same thing as Newton, basically force times velocity, right? That's all power, okay? And if you divide all these changes in kinetic energy, change in potential, change in dissipative energy, you divide by time and make those time increments infinitesimally small, so you're considering them at one specific particular instant, then this equation is true. Now we've changed the units. This is literally external power equals all these internal, the changes in kinetic energy, potential, and dissipative energy in the mechanism. And right, so you can see how that, hopefully you can see how the power equation derives from this. Now this is the one we're going to use. This is the useful one. That's the whole point of topic 6. Okay, so let's look at each one of these parts of this equation, because you're going to need to use it. It's a very powerful equation, no pun intended there. That really wasn't funny, but I thought it was. So say the input variable is phi, is the input variable, okay? So that's like, usually we're used to an input variable of like omega 2, right? That's the input link omega 2. So just pretend that's phi. The reason we make it phi is because the input variable, if it was a slide or crank, might be r. You might be linearly translating something. So we're just going to say the input variable is phi, okay? And it really doesn't matter what it is. It's just a general input variable, and this works for any mechanism. Okay, so let's look at power. We're going to see the P in box. We're going to look at power, and we're going to turn it into kinetic or kinematic coefficient land here. Okay, so the power due to torque. And by the way, this is really confusing. This didn't come from my slide deck, but if I had done these slides differently, they define T as kinetic energy. I probably would have called it K or something. Of course, that might have been confusing with stiffness. But, the T up at top there, and from previous slides, was the kinetic energy. But here we're suddenly making T the torque. And you'll find later in the lecture it switches to M for moment. But if you see an M, that's moment. And if you see a T with a line under it, the vector, that's torque, and the same thing, right? And so here the power is torque times angular velocity. Okay, you know that's angular. That's power due to angular, rotations. And you dot product, then you take the magnitude of this times the magnitude of this. And remember, for planar scenarios, you don't really need a dot product. You don't see any cosine here because they're both coming out of the page, and the angle between the two is 0, so the cosine of 0 is 1, right? So you take the magnitude of that times, just angular velocity magnitude, which, by the way, if you recall, is theta j prime, which is the first kinematic coefficient of that output link j, which is, remember, d theta j divided by d phi, if that's the input variable. And so if you times that by phi dot, which is d phi divided by dt, again, I'm drawing from previous lecture stuff, this will equal omega j. So this is just, hopefully you remember, if you take the first order kinematic coefficient, times it by the input variable, it'll equal the output angular velocity, omega j. So this equals that, right? But we're using kinematic coefficients, okay? Okay, so now if you want to find the power due to a force, okay, even for planar scenarios, oftentimes the path is different than the direction of the force, so you really do need to use the dot product of the force with the velocity at some point P, which is the point where the force is applied. Remember, the force itself, that vector, only tells you in the magnitude direction. It doesn't tell you where it's applied. But that's contained within the velocity of the point P. That's where it's applied. Okay, so if you definitely have to take the dot product of that even for planar scenarios. And to do that, remember, dot product, you line up corresponding coefficients, or you take the corresponding components. You take the two x components, multiply them, add it to the two y components, add them for planar scenarios. So it's basically this. But notice the trick here. We took the first order kinematic coefficient of point P. Okay, and here's the first order kinematic coefficient of point P of y, so there's x and there's y. And if we times both of these by the input variable, those will be velocity of P in the x direction, velocity of y in the y direction. Okay, and by the way, this whole course builds on itself. Of course, you can't do velocity analysis till you do position analysis. You can't do acceleration analysis till you do velocity analysis. Well, you can't do these power equations until you've done position, velocity, and acceleration analysis, and you have the velocity and accelerations of a point on the mechanism, specifically the centers of mass. So you'll see that in a bit in future examples, but you'll recall from past lectures I taught you, once you've done these analyses, position, velocity, or acceleration, how to find the velocities or accelerations at a point. And the point of interest for all these things is going to be where the centers of mass are. So you can find, or in this case, sorry, that's for future stuff, but in this case, where the point of interest is where the force is applied. So here's the first order kinematic coefficient for both x and y of where the force is applied. And we're going to assume you already know that from your previous analysis. Okay, so that's power. Okay, so now let's look at the other side of the equation. This first one, remember that T is kinetic energy, so the change in kinetic energy. Okay, so consider the kinetic energy of a single link J. All right, so you've got a link J, and remember that's the kinetic energy equation, the linear and angular component. Okay, so let's write it in kinematic coefficient land. Okay. Remember, if you take the first order kinematic coefficient, the x of the x component, and you times it by phi dot with respect to derivative with respect to time, you get basically the velocity of that x component at the point g. Okay, and same thing if you do the same thing with the y component, and basically if you do this, pull that in and notice that's squared, you could imagine each component squared adding together. That'll be the square of the total velocity at the point.